start recording, and we'll start. So today, I didn't prepare much, and maybe we should have just not met, but I guess people are so excited that we'll talk about some. I'll try and tell you two things fairly quickly, and this will be more of a teaser for the reading group that's going to happen in the summer. This is still very relevant to quantum mechanics, and we'll see in what way, but we'll study it more deeply over the summer whenever we do the bigger reading group over the summer. Okay. So let's what did we achieve in previous? We've defined a new type of space, right? What kind of space? What kind of space did we define in the last couple of weeks and study in some detail? Pardon? An inner product space, correct. An inner product space. This is what we kind of looked at, right? And we talked about, an inner product space, it has this, some interesting things. What is the main thing about an inner product space? It has an inner product. Very good. So an inner product space is roughly, I have a vector space, and then I add an inner product. Okay, beautiful. So when we were in our linear algebra course, we had vector spaces, okay? And we said we have vector spaces, and we want to study how vector spaces compare to each other. Do you agree? And so what did we use to do that? So I had vector spaces, and so naturally with vector spaces I had something else, and I wanted to study that additional something else.
Linear maps?
Linear maps, good. So I wanted to look at linear maps. So before, kind of without the inner product, I had a vector space. And therefore, I wanted to study maps that preserve the vector space structure. This was the logic. I have a vector space, it's some set with some structure, so let's study maps that preserve set structure. Okay. So now we have an inner product space. So now I want to study what kind of map? A map that what?
Preserves inner product space structure.
Very good. That's exactly right. So, and actually, we're not going to, let's make it a little bit simpler for me, because I didn't prepare. And we're going to study maps from the vector space to itself that preserves the inner product structure. So the new question. We always want to be always want to ask a question and try and answer it. Asking a question is very difficult. Answering a question is often easier than asking a question. I don't know. Right? Yes.
So just to make sure, will you please repeat your last sentence again?
So I said, before we had a vector space structure and on some set, and so we wanted to study maps that preserve this structure. So now I have an inner product space. So I want to study maps. So this is from V to itself, because I'm lazy and don't want to deal with with something that I haven't thought about for more than for a while. But so we want to study maps in principle from any two inner product spaces, but we'll restrict ourselves from V to V that preserve the inner product space structure. This is what we want to do. Very natural thing to do. Okay, but this is gonna steep. It's gonna be very steeped in a bit. So okay. I wrote down a sentence. So now your first question about the sentence should be, a sentence is some collection of words that I put together, but
Formalize it.
yes, in other words, I wrote down some words, but what do these words actually mean?
You want to investigate linear transformations.
Well, okay, this is a good question. So here I said that I want to preserve the inner product structure. Okay. In principle, on this thing, I have two kind of separate things. I have a vector space and a vector space structure. And in some sense, I can think of the inner product as something a little separate, right? Because if I wanted to, I could kind of forget the vector space structure, and the inner product would still make sense as something that takes in two vectors, outputs a number, right? The properties where it's like v plus u inner product, but like the linearity properties might not make sense, but the function itself would still make sense. And so the question, first interesting question that you could ask is, well, do these, first of all, okay, if I want to study the maps from V to V that preserve the inner product space structure, I want to say, what are these maps, right? That's one question. How do these maps look like? And the one question I could ask, okay, what if I looked at maps that preserve this and this versus maps that preserve just this? Okay. The surprising thing is that maps preserve just this end up being linear, which is a little surprising. Well, maybe not that surprising, because in some sense the inner product has linearity built into it somehow. So it's not completely surprising. But the point is that maps that preserve this structure, and this is the other thing. I still haven't said what I mean by preserve the inner product structure. This is the first thing we should first say, what it means to preserve the inner product structure. Once I do that, once we agree on what it should mean, then we can actually go ahead and try and figure out how these maps kind of look like. And we'll get that those maps have to be linear. So kind of if I just worry about this, I'll get that the maps have to be linear. So I'll be very happy. And then I'll make a small comment about some time evolution, and I'll say how this might relate to something else. Okay. So actually, one thing, why am I most interested in maps from V to V? Because in quantum mechanics, I will be kind of working with the states of my system will come from a vector space, and so I'll be interested in things that go kind of from the same vector space to the same vector space, because it describes like one system, and it's not like I'm going to want to be it's okay. Like this is because this is what's most relevant for us in quantum mechanics for the moment. So I want to study, okay, so first is, what does it mean? What does preserve, inner product structure mean? So I will define it in the following way. I'm going to specifically look at the maps. Sorry. The maps U. Yes, U from V to V, such that let's take some two vectors V and W, take their inner product. Then this inner product will be the same as UV, comma UW, for any VW in the vector space. Okay. So let's stop and think about this. And you're going to just tell me some answers, and then we're going to realize something. So I'll give you another moment to write things down. Just for the people on the video. Okay. So in what sense does this preserve the inner product space structure, right? Well, yeah, in what sense does this preserve the inner product space structure? Try and say it in words. Yes.
Yeah, it doesn't change either the inner product in some sense.
Yeah, so if the inner product between V and W was some number, if I apply the map both to V and W, then the inner product stays the same. Okay, like that's literally what it means. Now, let's think about this in an example. I should maybe write this down, but I don't want to stand up. Remember we had the example of R2. R2, just a plane, it had some inner product, between, it had some inner product defined on it. If I had two vectors and I took the inner product between them, what did the inner product really tell me about those vectors?
So in some sense, preserve the geometry of our space, right?
Give other people a chance to answer. So, yes, but give other people a chance to answer. So the question was, if I have two vectors, I take the inner product between them, what does that tell me in R2?
Can I take the example of dot product?
Yeah, I'm telling you, it's the dot product. You have R2, you have the dot product. You take the dot product between two vectors. What does it tell you about those two vectors and how they relate to each other? The dot product of two vectors is?
Magnitude A times magnitude B times cosine theta from
Yes.
one of the vectors?
Yes. So the inner product kind of tells you the angle between two vectors. Do you agree? Okay. Roughly.
Okay.
And so this kind of transformation, it preserves the lengths of each vector. Do you agree? Because if I set W to V, right, this is true for any V and any W. Do you agree? So if I set W to V, I get the length is preserved. If I set V to W, I get the length is preserved. And so I get that then, if it's V dot W, length of V times length of W times cos of the angle between them, I know that length of V is preserved, length of W is preserved. Then I know that this also preserves what's left? There was length of V, length of W, and the angle. Yes. So in R2, for the dot product, these should be transformations that preserve lengths of vectors and also angles between them. What are those transformations?
Rotations.
That's exactly right. And maybe reflections.
Okay.
Right? You might want reflections. But actually, do I want reflections? Yeah, I think reflections still work.
Translation? Or
A translation doesn't work. Because it will not preserve the angle between things or the length. Right? Like, if I have, this is my vector, this is my vector. If I translate both of these by this amount, right? This is now my vector, and this is now my vector. It got longer, the angle changed.
You can't move zero.
Yeah. 0 is fixed. Well, 0 would move, but the inner product, would. And that, yeah. And then the other thing is 0 would get moved, right, to something non-zero, and so before the inner product of 0 with itself was 0, but then all of a sudden you'd get that the inner product of 0 with itself is non-zero, and so that would not work. That does not preserve the inner product structure. Okay. Does this? So already in R2, we know that the answer should be like rotations with reflections and maybe combinations of rotations and reflections. Do you agree? So here we already have an answer of what to look for. But, okay, that's good. I mean, everything I'm telling you right now was a tutorial problem. It was a bonus tutorial problem. Solutions for which are posted. Very good. Sorry, let me just double check that. Hold on. Okay. Right. So we see that rotations and rotations do this, right? They do this. But one thing that's maybe not immediately obvious is, are rotations linear maps, right? Because well, if you know the answer, yes. But I feel like, to me, it's like rotations are like what? A linear map is something that, like, if I take this vector, I take this vector, and then I add them like along a parallelogram, right? And I get this vector. Then if I rotate, then the sum of the rotated vectors is going to be this vector rotated, right? But that that sounds like there's more than one step to that proof. Like visually it's kind of obvious, but like, what if something went wrong? Of course, nothing goes wrong, and so let's prove it. Let's prove that. Good morning. Let's prove. We're talking about a tutorial problem from a while ago. Maybe you were there when we discussed it. We're talking. I want to prove. Yeah, that U is U is a linear. So for the people who came late, a rough summary. Back in the day, we had vector spaces. They had a vector space structure. So we wanted to look at maps that preserve the vector space structure. Those were linear maps. Now we have an inner product space. It has an inner product space structure. So we want to look at maps that preserve the inner product structure. We define a map to preserve the inner product structure is when it does this. That U is a map from V to V. So we're specifically looking for maps from V to self. But if we say it preserves the inner product structure, if V inner product W is equal to U applied to V, comma U applied to W inner product. So if the inner product used to be this, then it's still this. Okay. And now we want to show that if a map does this, then it necessarily has to be a linear map. Okay. So what do I want to do? So what do I want to show? I want to show that T of U plus lambda V was equal to, well, let's do W. T of W plus lambda V was equal to T of W plus lambda T of V. Right? This is what I want to show. Oh, sorry, not T, U. Lies. I was using U. Do you agree? This is what I want to show. But this is completely equivalent, by definition, as showing that the norm of U applied to W plus lambda V minus U applied to W minus lambda U applied to V has to be 0. Right? Because only the 0 vector has 0 length. Only the 0 vector has 0 length. And so if that vector is 0, then those two things have to be equal. And so that's an equivalent thing to prove. Do you agree? Very good. Okay, but now this is a very easy proof. Maybe I should just leave it as an exercise. And then we'll be done in like 6 minutes. Because I don't have anything else to say. But maybe, I don't know. It's just a calculation, right? All I will do is okay, if this is 0, then this is equivalent to the thing squared being 0. Do you agree? But the thing squared is just U inner product V plus okay. So I want to show that this thing is 0. I mean, all I did was just rewrite the same thing. Squared. Okay. And now what I will do, so I don't want to do this. What I'll do is I'll use like linearity and from each of the entries, and I'll just expand everything. Do you agree? And I'll just tell you what I get in the expansion. I mean, it's literally like opening brackets, like, right? Because it's linear in each entry. If I multiply two numbers, right? Like if I do like, what is it called, FOIL method or whatever. Yeah. When I multiply two brackets, then multiplying two brackets, that's something that's linear in the entries of the first bracket and the second bracket. Do you agree?
Yeah.
Like and so when you do inner products and expand them, it's literally just like opening brackets for multiplying numbers. But instead of brackets, I write, I have a first slot and the second slot. Okay, who cares? Honestly. Okay, so let's do this with this, this with this, this with this, and then I'll have the conjugate of that, and then okay, so let's write it. Minus inner product u w minus u.
Is this what you meant by when you say like the inner product already has like linearity built in?
Yeah. Well, actually, this is not. Yeah, this is yeah.
Okay.
This is a property of the inner product,
Mm-hmm.
and it's built in.
Okay.
That's right. Maybe lambda bar.
There's supposed to be U in front of that.
Wait, sorry. I don't know. This is not lambda bar necessarily.
Such that
U.
shouldn't it be
Actually,
like being
yeah.
applied to that?
To what?
Wait, so here, such that.
Oh yeah.
Such that
U
v inner product w is equal to u applied to v inner product u applied to w.
Oh, I see.
If the angle between two vectors was this, after I transform them, the angle is the same.
I think you're on the last one.
So actually, this shouldn't be here. This should really. Actually no, that's okay. Lambda bar uv. So that's me doing this with this with this with this. Then I need to now write down this with this with this with this and this with this with this with this.
And terms cancel.
And terms will cancel, and then we'll see why they cancel. But you know what? For the fun of it, let's write everything down. I'm literally just writing stuff down. Like this is.
Well, mathematics is all about.
Yeah, but this is not the fun kind of thing to write down. This is like, I'm learning nothing right now. Well, I'm learning how to expand brackets. That is in fact a very important skill, which many don't have. But that's okay. Well, maybe it's not okay. Maybe you should know how to expand brackets. This one with this one. And okay. I just expanded the brackets.
Or I was talking about whatever that is.
Oh, that's yeah, that's what I'm drinking right now. It's getting more and more bitter every time I pour myself a little bit more. Still enjoyable. It's very dark. Okay, but now, what can I do? What's the next step? In
Can-
every, yeah.
I was gonna say, can you, inside every, how do we call this?
Inner product?
Inner product, there's like U times like W plus lambda V, can we
Yeah.
like expand those?
Well, no. This one I cannot expand. Remember, my whole point is to show that I can expand like
Okay,
this.
yeah,
Do you agree?
so, okay.
So that's the whole point of what we want to show. But what is something that's true about U? In fact, the only thing we know about U. There's like 4 colors on the board.
Linear.
Pick a color.
Inner products with it.
Yes, that it does. U does this. This is all we know about U.
Yeah.
Okay. So if U does that, look at what I have in every single bracket.
U.
In every bracket, I have U applied to something, inner product U applied to something. So I can get rid of all of the U's everywhere. Do you agree?
Wait, there's a bracket.
Oh no, I have a bracket missing.
No, I'm just trying to make sure if that closes there or closes.
Oh no, it closes there or not there. No, this makes such a big difference. Maybe there's more errors. Okay. But the point is, I get rid of all of the U's everywhere. I can get rid of them by their property in yellow here. Great. Now that I've gotten rid of all the U's, I'll just have omega plus lambda V, W plus lambda V, inner product W plus lambda V. That's just sum. So that I can further expand. And I'll have W inner product W, which is going to get cancelled by W inner product W. Maybe this should have oh no, I'll have 2 of them, but then there'll be like, point is you expand this out and then it will cancel out.
Inner products are symmetric. So,
Almost. You get a conjugate.
Yeah.
that's what you have lambda.
And that's why I have lambda bars.
Okay.
Okay, the point is, if you now sit down, get rid of all the U's, expand everything out, you get 0. I'm not doing that.
I should probably write that
And please don't do that now. Just write that this equals to 0 because you apply this property and expand and everything cancels out.
down. Oh. I mean, just to be clear, conjugate of 1 is 1.
What do you mean conjugate of 1?
Oh,
Oh yeah,
that's
conjugate
a
of
real
1.
number.
Conjugate of a real number is a real number.
Okay.
Conjugate of a complex number is the conjugate of the complex number.
Okay.
Okay. Do you agree?
Yeah.
Okay. So in fact, what we just proved, one of the kind of corollary rotations are linear transformations. Okay, but this was a tutorial problem, right? You know this.
Yes.
Good.
We should see FIS as well, like what, chapter 1.3.
Hmm?
This was on like the textbook as well.
I don't know. I didn't read your text. I read Exler.
Maybe I should use that instead.
Everyone should read Exler. Good. Can I now? You know what? Let's erase this. I will erase this because this is simply not very important. And now I'm going to. Okay. I'll make some statements. So. There's particular things where we give things particular names. So we define ON, this is not theta, this is O not theta, to be the set of maps, let's call them O from Rn to n, okay, such that they have the property. Maybe I shouldn't call this O, maybe I should call this, I don't know, whatever, let's call them U still. Whatever. On is all the maps on Rn. Sorry, where this is the usual dot product. Okay. So On are all of the maps that preserve the dot product on Rn. Okay, this makes sense?
Yeah.
So this will be rotations and reflections and combinations of rotations and reflections. So SON. So I'll say this, but it won't make sense what it means, but you should still write it down. Is all the maps in On such that U preserves orientation. In other words, the determinant of the Jacobian is greater than 0. Okay, but
Sort of your-
don't worry about that. Just write down some of these words.
Question.
Yes.
That is SO.
SON.
Okay.
So this is called orthogonal group,
Mhm.
I think. This is called the special orthogonal group because I pick up, only select ones from here. Yes.
Dot product in higher dimensions is just magnitude of all your vectors.
Xi dot Xi.
It's projected.
What? No. I have a vector, v1 e1 plus whatever, and then I have another vector w1 e1 plus whatever.
Mhm.
Then the dot product is just going to be v1 w1 plus dot 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 vn wn.
Oh.
Dot product. I multiply entry-wise
Okay.
Oh,
in the
wait,
standard
yeah,
basis.
wait, I
The dot
missed-
product.
yeah, yeah,
Yes.
The
yeah.
angle thing is only in R2.
It still works in R3 and in R2 and in R3. It's just that in R4, what does it mean to do angle? And then you just define what it means to do angle in terms of the dot product.
Okay.
Because it makes sense how to compute the dot product, and from that you compute the angle.
Thanks.
So it's kind of you reverse what is more fundamental. We now think of the inner product as more fundamental.
Does it let du greater than-
Determinant. Determinant of the Jacobian of U, but whatever. Actually, one thing that I should have said is you can immediately see. So these maps are linear. Do you agree? We proved that these maps are linear. It's now obvious that all of these maps have to be invertible. Why? Why is it obvious that all such maps are invertible? So all maps that preserves the inner product space structure. No. What does it mean for a linear map from a vector space to itself to be invertible on finite dimensional vector spaces? Bijective, but that's equivalence. If you're going from V to V, that's equivalence to?
Just injected.
Yes, injective.
Existence of an universe.
Hmm?
Existence of an universe.
Just
I need
injective.
something easy to check. So injective, but inject.
Only the 0 goes to 0.
Only the 0 goes to 0, right? If something, remember, 0, inner product of 0 with anything else is always 0, right? So yeah, 0 inner product with anything is always 0. And so if I was to map something non-zero to 0, I'd get that something that had non-zero length all of a sudden has 0 length, which violates. So I get that all of these are actually immediately invertible, right? And I mean, yeah, so now you got for free that every rotation is invertible. Okay, but you knew that. But, still, we've at least proved it now.
Ooh.
Yes,
Third question. Are there only rotations and
reflections.
across even
I think even in higher dimensions, I think that's still true.
only.
Yes, I think that's still true. Checking that, we're not going to check that.
Wait, what is the second set? Exactly? Preserves orientation.
It preserves orientation, meaning that the determinant
Oh, okay,
of the
those are
Jacobian is
same.
greater
It's
than
not
0.
like it needs to have that
So
and-
i.e.,
Oh.
i.e., the determinant of this is greater than 0.
Okay. I thought it was like two things that it had to
Yes.
satisfy, and I didn't know what the second. But they're just the same.
Let's
thing.
not talk about this. So now we're going to define, and this is where it gets confusing. We're going to define un. UN, and this is going to be all maps from CN to CN, such that they preserve the complex inner product on CN. Where this means, V1 W1 bar plus, Vn Wn bar. So the usual inner product on complex on CN. Okay. I will now erase this board. Okay, and so what names did you have? ON was the orthogonal group. I think it's, wait, is it called the orthogonal group? Yes? Okay. SON is the special orthogonal group. UN is the
Unitary?
unitary, that's right. Unitary group. Okay, and there's also a special unitary group, but which is also the same idea. It preserves orientation, but I don't want to. I don't remember. It's. Well, yeah, I just don't want to discuss. Oh wait, sorry. Is it just this, or do I need something like U transposes the identity? Or I think I get this for free. I think it follows. Yes. Okay. Good. Okay. I could define SUN as things where U dagger is 1, but okay. I don't want to write that right now. So yes.
This is groups, as in like abstract math group?
Perfect. That was the next question I was going to ask. Are they?
What's the definition?
Yeah.
Oh, do you not remember the definition of a group?
Like it's basically has everything except commutative, right?
Not necessarily. So I have a sense in which to multiply two elements together. I have inverses. I have an identity. Multiplication is associative, but maybe it's not commutative. Okay. Can I compose two rotations together?
Yeah.
Okay. Hopefully composing rotations is associative. It is. What else? Is there an identity rotation?
Yeah.
Which is the... Yeah, exactly. No rotation is the identity rotation. And then do I have inverses of rotations?
Yes.
Yes. In fact, we already proved that everything has an inverse, right? Because we proved that they're... we said it in words.
Wait.
Yes.
What's the zero rotation?
The zero?
Or does the group not have a zero?
The group has an identity element.
Okay.
The identity element is the identity map.
Yeah,
Do
it
nothing.
stays the same.
Everything stays the same. Yes.
So
It's not a zero in the sense that. It's the identity in the sense. Fine, I'll write down.
It's more of a one.
Hmm?
It's more of a one.
Yeah. What?
It's more of a one.
It's like.
There's only one operation with this one, like multiplication.
And then there's a one.
Okay.
I have something G cross G into G, right? A dot, such that there exists an identity, meaning that E dot G is equal to G for all G, right? Then the second property is that for all G exists a G inverse such that G inverse equals G inverse G equals the identity. And then the third property is that A B dot C is equal to A dot B dot C. So the associativity. Okay? This is what a group is. And this is indeed a group. All of these are groups. In fact, what we'll see in a second, well, we won't immediately see it, it's not going to be obvious. But it turns out that these groups can be given a manifold structure. And so they're actually what's called a Lie group. And then, if it's a manifold, right, then it means it locally looks like Rn in some sense. It locally looks like Rn, meaning that it has to have some tangent vectors. Okay? And these tangent vectors are precisely the Lie algebra of the Lie group. Okay? I think I also talked about this in one office hour, but maybe not precisely. And this, we will have a reading group on this over the summer. Well, maybe some of you will not be here, but I will have a reading group without you regardless. You're not necessary for me to have a reading group. But you are, of course, all welcome to join. Pardon?
One person is necessary.
At least one.
You overestimate how much I need an audience.
I would love teaching online,
Okay.
bro.
No, I won't teach online. I'll just have an empty room.
You can teach online and record the empty room.
True. Okay. Right. Okay. So now we'll do the thing that kind of hints at something is a Lie group, like something, and we'll see something. I was going to talk about Pauli matrices, but maybe I don't want to. Maybe I'll leave it as an exercise for the reader. That's what we'll do. So, remember, we're doing this all for quantum mechanics. And in quantum mechanics, at some point, we're going to want to talk about things evolving with time. Do you agree?
Yeah.
So, for whatever reason, we're going to have some complex vector space, which is going to be probably isomorphic to Cn, with an inner product structure on it. And I'm going to have some unitary map in the orthogonal group. Oh, in the unitary group. On Cn, right? So U takes Cn into Cn. Okay, this will be some math. But actually, what I'll want to have something change over time. So actually, I'll have a family of maps. A parametrized family of maps. Okay? U of t, right? So for every point in time, I have a map from Cn to Cn. So it's kind of like R cross Cn, Cn, right? So for every point in time, I know how to send a vector to some other vector in a way that preserves the inner product. Okay? And we can actually talk about a smooth family of maps. Okay, we can talk about how to, define derivatives in the space of operators and whatnot, and that's kind of easy to do because whatever. But one way you can think of this, and let's think of it as the easiest way to think of this, as U of t. This can be in Cn. This can be written down as some matrix. Do you agree? Yeah. And the coefficients of the matrix are smooth functions of t. Okay, this is something you can understand.
What is a smooth function?
Infinitely differentiable.
Oh, okay.
You can differentiate it as many times as you like.
So like a polynomial.
Not necessarily. Not all smooth functions are analytic. Not every smooth function I can write down as a Taylor series. And you'll see an example of this in 157. It's something like e to the minus x squared, but then divided by.
E to the power of
It's one of those, like,
minus
weird
1 over
examples.
x.
Pardon?
E to the power of minus 1 over e.
Yeah.
It's one of those
So
weird-
exactly, it's e to the minus 1 over x and then divided by x. Like
No,
this?
that would be never enough.
Huh?
No, just that.
Oh, just this?
Yeah.
Yeah,
And
I believe this.
From x for positive x, for
Negative.
non-negative x it's 0.
Yeah, there we go. Well. So this is an example of a function where its Taylor series is, I think, identically 0. So as you approach 0, all of its derivatives are 0, but clearly the function is not 0 everywhere. So its Taylor series is at 0 is 0 everywhere, but then, and it's still smooth. But it's not the point. This is an aside with something you have to learn in 157. But if you were to look at once differentiable, so in complex analysis, you're going to look at functions of a complex variable. And if a function is once complex differentiable, then it's infinitely differentiable, and even better, it's analytic. It's crazy. Complex numbers are crazy. Like in real numbers, I like have to fight for everything. In complex numbers, I get things I didn't even want for free.
No, they're imaginary.
No, but they're actually very real. Like it's insane.
Sorry.
Okay. Yeah, okay. Do you agree with this?
Yeah.
So now I can take a derivative of this with respect to time. Do you agree? And how would I take this derivative? Well, I mean, I can have some components. I can take the derivative component-wise. Okay? So let's figure out how this derivative looks like. And to do this, we have to use the property that U satisfies. Do you agree? And U satisfies a fun property. So I know that U of t, V, U of t, W is always equal to V comma W for any t, right? Because I said let's let U be this thing that does this. It satisfies this property. Yeah. I'm not going to the board today. Very sad. I don't drink, but I'd love to chat with the other physics people on a Friday at 8 p.m. Okay. So we have this property. Do you agree? So I can take the derivative of this now with respect to time, because it's some function, some scalar function. Okay. What is the derivative of this whole thing going to be with respect to time?
Partial that, partial t.
Good, but I want a number. There's two numbers. Come on, guess one of them.
1.
There's another number.
0.
0. Can you please look at this equation and look at the right-hand side? Does the right-hand side depend on t?
No.
Also 0.
So of course it's 0. It's constant in time.
Oh.
Okay. Thank you. So I have the condition that the derivative with respect to time of U of t V U of t W is 0. Do you agree? Now I'm going to use some facts, which I'm not going to prove, but you're going to believe me that they work. We're going to take the derivative. And it's not by intimidation. Are you really intimidated right now?
Yes.
Okay. I'll cut that out of the video. Don't worry. No, I won't. I am too lazy.
By superstition.
So this thing is linear in each entry, right? And as you remember from one of the the office hours, a derivative is the best linear approximation. So I'm going to kind of, so because this is linear in each entry, I should be doing like, this is kind of like multiplication, right? And for multiplication, I have the product rule, right? Where I take the derivative of this times this regular plus the derivative of this times this regular, right? The point is, it will still work here as well. And I mean, you can just check it by like taking the limit as t goes to 0, whatever. I just don't want to do that. I'll just tell you that this is what it is. That I'll have u dot at t applied to v. And also v and w are constant in time, so I don't have to take the derivatives of them. U of tw plus u dot, oh, no, what, u of t, hold on, u of t v, u dot of t w. Good, okay, there is no dot here. We agree with this, yes?
Yeah.
So, the question, if there's t, well actually maybe there's less and less t. There's very little t left. In fact, there's no t left.
Don't worry about that.
I was not worrying about it. I'm more worried about myself not having more tea to drink. Okay. What was the question? The question was, figure out what was the question? The question was to figure out what u dot looks like. Right? I see. So let's try something. Okay. Let's try this. Let's do u dagger of t. U dot of t. V. Dagger was the conjugate transpose.
What is
Did I miss this? Was this last week?
This is last week.
Oh.
Okay. Right. What? None of you were here.
Go on.
Conjugate transpose means I transpose and take the conjugate of every entry. It's related to the adjoint operator. The adjoint, so if I have, if u is from v to v, right, then u dagger is also from v to v, but such that v u vw is equal to v u dagger w. So u dagger is an operator that does this.
Oh, okay.
Okay, it kind of, I flip it on the other thing and then it preserves the whatever it preserves. So for every u, there's an associated u dagger that I can kind of swap between the entries. Yes. Okay, I remember now the point. Okay, very good. Good. Yes, this is exactly what I want. Almost as if like I did not mess up a 3-line proof. Beautiful. So now I can do the same thing and take the dagger of the derivative and move it here. Right? So dot dagger. Inner product W. Okay, actually, wait, this is going to be interesting for the two of you as well. Because now you're going to learn something about the Schrodinger equation that you always knew. Okay?
Yeah.
Good. Right. But and we said that this expression is always 0. Do you agree? This expression is always 0. And this expression is always 0 for any v and w. But this implies that u dagger of t, u dot of t, plus u dot dagger of t, u of t, is equal to 0 as operators, right? Because this is 0 for any v w, okay, you can check that this implies this. It's actually kind of a bit difficult to check, but you can, well, if you have the Riesz representation theorem, it's trivial to check, but yeah. Right, because I can combine these in what way? I can combine these as u dagger of t, u dot of t plus u dot dagger of t, u of t all applied to v, like this. Okay, so I have like this single operator acting on v inner product with w is 0 for any v and w, so this thing has to be 0. It's actually, well, okay, I won't say. Okay, I have this. Now I'm going to okay. Now I'm going to impose a certain condition. Okay? The condition I'm going to impose is, I should have imposed it at the beginning, but I'm going to say that suppose that u at u of 0 was the identity. So meaning that initially nothing changes, but then over time things kind of start changing more and more. Right? Like it kind of makes sense. At the initial point in time, everything is how it is at the initial point in time, and then things only start changing as time starts going. Okay? So then I get that at t equals 0, I just plug in t equals 0 into this expression. Okay? And at t equals 0, u of 0, so I just plug in t equals 0 ever. U of 0 I said is the identity, so the dagger of an identity is still the identity. This is the identity, and so I just get that u dot at 0 plus u dot dagger at 0 is equal to 0. Okay? So we got a non-trivial condition on the derivative of this kind of map. Do you agree? Yes.
That is 1, but in math language.
This is the identity operator, the identity matrix.
Okay.
So this is like an assumption I told you, like suppose this, then this. Yes. But so what do we get about the derivative? We get that the Hermitian conjugate of the derivative is in fact minus of the derivative itself. Do you agree? So this kind of matrix, u dot, this is called what, anti-Hermitian or something? Is that right? It's called anti-Hermitian. Very good. But now, let's do a little substitution. A very, very simple substitution. So I have this object, u dot at 0. Do you agree? Let's define a new object, and now I'm going to mess up which way the minus sign goes. But let's define a new object called h at 0, which is going to be equal to I at u dot at 0. Okay, so I have this u dot thing. I know what it is. Let's define h to be I, at thing. Okay, do you agree? So this means that u dot at 0 is equal to minus I h. Well, let's just call this h with this. Minus I h, and u dot dagger is equal to I h dagger. Do you agree with this?
Yeah.
Perhaps people might see where this is going. Well, for the people who were here yesterday, well, no. You were here for the spectral theorem discussion, right? Oh, right, because that was last week. Damn. Well, no. I think you guys were there. And surely you guys know what the spectral theorem is. Right?
Which spectrum?
Great question. The one that was discussed last week for self-adjoint operators over a finite dimensional vector space, complex finite dimensional vector space, not the other ones.
Our Bible.
Okay. The spectral theorem was that, let's finish. I want to leave because I also have to do the workshop for you now as well. Okay. So I defined this H thing like this by just taking this and putting an I in front of it. Do you agree? But now remember, I have this condition on the U. Okay. So this came from just how the property of the dagger operation, whatever. Don't worry about it. What's important is now I can write this, but write it in terms of this new H thing I defined. Do you agree? Yeah. And I'm going to get, U dagger of, so I have U dagger is equal to minus, U dot dagger is equal to minus U dot. Do you agree? U dot dagger is IH dagger is equal to minus U dot is equal to minus of minus IH. Okay? The I's, as you can see, cancel out, and therefore we get H dagger is equal to H. Okay. For the people that were here last week, this is what kind of operator? Self-adjoint. Beautiful. Okay. So, for the people in the back, what does this explain in a trivial way about the Schrodinger equation that for some reason people say is very insightful, but it's not? People about the Schrodinger equation are often confused. Why is blank in there?
I?
Yes. Why is I there? I mean, this is why.
I asked myself the same question.
This is precisely why. Because you want to evolve along something that preserves probabilities, so it preserves the inner product. So the thing, and then you take the derivative of the thing you're evolving by, and you get the derivative has to have this kind of condition on it. Do you agree? The derivative is has this kind of condition. So in the Schrodinger equation, you write what? You write IH bar partial t. Sorry, no. You get that partial t of whatever is IH bar of whatever, right? You write something like this down, right? But you really shouldn't think of this as IH. You really should think of this as something that is anti-Hermitian. Do you agree? It's not that there's something, the reason why we want to worry about H is because, okay, this thing I can say is my U dot, okay, and it is anti-Hermitian because it better be because I want to preserve probability, right? The reason why we write it as IH instead of this anti-Hermitian thing is because we want H to be self-adjoint so that we have the spectral theorem. The spectral theorem. So for the people who don't remember what the spectral theorem is. The spectral theorem was, so if H is equal to H dagger, remember, so i.e. H VW was equal to VHW for all VW. So if this is true, then there exists an orthonormal basis of eigenvectors of H. Okay, you have to absolutely know this for everything we're going to talk about in the future. I mean, it's a very short video from last time, and it's a one-line statement. Surely you can understand think about and understand a one-line statement. There's only so many words that you have to figure out what they mean.
Are we still in the realm of intuition, or?
We're always in the realm of intuition. There's nothing that's not intuitive.
Just have to think harder.
Yeah, that's exactly right. Sometimes you don't have to think harder. Sometimes you just have to think for a little bit longer. You know? But at the end of the day, you should just find a way in which it's easiest to think, right? So think about many simple things instead of a hard thing. Right? For example, what letter is in front of you? It's a pretty good thing to think about. Okay. Hmm? Yeah. Okay. Do people in the back understand this point about I and H now? Right. So the thing about the Schrödinger equation, the I is not important. What is important is that the equation is linear. That's what is really important about it. That it's a linear equation. The fact that there's an I is, well, of course there's an I, because I have the Born rule and I want to preserve the Born rule, which we will learn about next week. Oh, well, next week. Yes. What's important is that it's linear. And there was a colloquium last semester which actually talked about this precise thing of, what if the Schrödinger equation was nonlinear? How could we try and study those effects? And then they had this or was that this other colloquium? Maybe that was a talk last year.
I don't remember.
Anyways, there was a talk in the last year which talked precisely about the fact that what if the Schrödinger equation was nonlinear? How can we try and experimentally test for that? And it was kind of interesting. But yeah, once we get to the postulates of quantum mechanics, we'll see that the thing that the Schrödinger equation brings is not the I, but the fact that it's linear. And the I piece comes from another postulate. But yeah, the point is that if you have something that some transformation u of t that depends smoothly on time, and it has the initial condition that at time 0 it's the identity. If you take its derivative at time equals 0, you see that the derivative has to be some skew symmetric matrix. Do you agree? And if you take that, multiply it by I, you get something that is self-adjoint, meaning that it has some orthonormal basis of eigenvectors, and the important thing is it has real eigenvalues. Okay, and then so last thing that I will leave as an exercise. Yeah, okay. So, yeah. I can define, no, sorry, it's not like this. I can define with lowercase fancy letters SU of 2, which are going to be, yes, SU2, but they're lowercase, more rigid letters. I don't know how to write that.
Is this the Lie algebra?
Yeah, this is going to be the Lie algebra of SU2.
Okay.
That's right.
Like a cursive S in French.
Yeah, you just write cursive SU.
No. Well, maybe.
That's my hack.
You're right. Sure, but I wrote this already, and so this is how it is now.
Okay.
You don't get to argue. Well, you get to argue, but you don't get your way. Okay, and this is going to be all linear combinations. Oh wait, no, sorry, lies. It's going to be all matrices, all 2x2 matrices. How do I write this? So matrices that have I don't know, 2x2 and have complex coefficients. I can't. I'm blanking, but whatever.
What's complex?
Yeah. So matrices that are 2x2 and have complex coefficients. This is what I mean. So this is the set of 2x2 matrices with complex coefficients, such that M is equal to minus M of the adjoint, of the Yeah, the adjoint. The adjoint of a matrix in this context is I do a transpose and the complex conjugate of every entry. Okay? And so what's the exercise? People in the back, what's the exercise? What's the exercise?
Its representations are like the solution to that.
Too much. Simpler exercise. Simple exercise. The simple exercise is so we now go up to here. Show that SU2 is actually can be written as x1 sigma 1 plus x2 sigma 2 plus x3 sigma 3, where all the xi's are real numbers, and sigma 1 is, I think it's like this. Sigma 2 is like this, and sigma 3 is, what is sigma 3?
1, -1, 0.
Okay, at least something that you know. Good. Okay. Yeah. Yeah. Yesterday, people were confused about that something is a letter. I don't know. Okay. Do you agree? Do people understand what the non-trivial statement is that you have to show? Now, yeah. So the argument: any 2x2 matrix with complex coefficients such that, whoa, sorry, this is a lie. Oh my God. There should be an I everywhere in front. Right. That changes because these are adjoint, but I want them to be anti-Hermitian, or whatever the words are. Sorry, there has to be an I in front of everything.
Why don't they just put the eyes in there?
Yes, but remember, so that's a great question. That's a wonderful question. The point is that for I sigma 2, the eigenvalues are complex. But for just the sigma, I have real eigenvalues. And things I measure in experiment are real numbers. And so while mathematically it makes more sense to think about I sigma 2, physically you always want to think about sigma 2 because you want real eigenvalues. And that's why this whole point is that physicists like to write the I separately so that, I times H has real eigenvalues. But IH is going to have complex eigenvalues. Okay. Good. Okay. Do you agree this non-trivial statement? Do you understand what the non-trivial statement is? So, but one thing that you can now kind of see is that SU2 is it's this like weird lowercase s. SU2 is a 3-dimensional real vector space. So 3-dimensional vector space over R. So it should be, in some sense, isomorphic to R3. Do you agree? So what's the dimension of SU2 as a Lie group? People in the back? Great. That's right. Yeah. See, he understands the rules of the game. The two of you, you don't.
This was not the game.
This is very much the game. Okay. Right, I told you this is going to be a quick 30-minute discussion. Very good. Very good.
Yeah, it was 30 minutes.
Yeah. Okay.
Like,
I think,
Certainly not.
yeah, this was at least an hour. But when I was exiting the room to get tea, I was chatting with someone and I told them that it will be an hour. And so I was right.
It's an hour thirty.
More than
An hour 35.
Oh yeah, so I told you it's gonna be in 30 minutes. I told someone else it's gonna be an hour. So combined, I'm correct. You know, okay. You have an exercise. You have a reading exercise for, you know, do the last week's thing. I think this is a good place to stop.